Yeah, so welcome to this evening's lesson. This is a free class from Mahadumia, and I think this is the third day for this free night class or for this free evening lesson. So the purpose for this evening lesson is, as I said, I think I said so yesterday. The purpose is such that we could be able to help you guys augment your personal studies. And probably if you've been studying and probably having difficulties to understand, we're trying to see whether we could help simplify the stuff such that when you go back to your own study notes, it would make more sense. So I'll be trying to see how I can use very realistic examples, like something that you can relate with, that you could easily memorize. And I'll also try using storytelling such that we would be able to grasp more, because I believe stories help to create more memories in our head. I remember when I was in secondary school. I say secondary school while I was in my university. Sometimes when I try reading something, so long as I try to understand it, I'll try to create a story around it. I taught some of my colleagues then, and I also would try to use the same idea, trying to use a story. It's easier for people to remember things with story. So I think I'll be trying to use that approach in this lesson. Physics is simple, I can say. It's simple, just needs, let's say, a little bit of your mind, a little bit of your head, and knowing how to memorize formula. So let's start. Today's lesson will be having to treat mechanics and properties of matter. So this is our first week's lesson, and it's a 12-week lecture or 12-week lesson, such that at the end of the 12th week, you will be able to have completed the entire syllabus. So meaning if you start with us today and keep up with us till the end of the 12 weeks, you would be able to cover your entire syllabus even before your exams. So that way you'll be able to have chance to probably do extra studies or extra revisions for yourself and try past questions as much as you can. And that's one of the easiest way to smash your courses. One of the things I did while I was in school was before the school resumes, I always would take the contents, as many as I can get, the lecture notes from previous sets for the next semester. So while people are on holiday, I would try as much as I can to study like that period. I would try to see how much I can finish the semester. I would look for the ones that I had, and they say these ones I had. I'll try learning them before the semester starts, and with one goal, so that I would deceive as many people as possible. It's funny, but I was always with that goal, so that I would deceive as many people as possible, such that when I'm done with the syllabus before the semester starts, when the semester starts, everybody will be like, "Hey, this one is hard. Oh, hey, this one is hard." I will join them. I'm saying, "Hey, it's hard. Oh." I've already taken a huge step ahead of them, and they will barely see me read. They will barely see me read. I would just make small revision because I've already studied this thing. I'll make small revision. Then by the time results come out, they'll start being like, how is this thing simple? Because by the grace of God, I was among the best in my department. Not just among, I was the best in my department. So that's just my secrets, or one of my secrets, if I'll say it that way. So if you take that to mind, it's going to make it easier for you. You can even watch movie during your whole semester. People will be wondering why you are watching movie, but you've done the real work before then. People always try to read close to exam, but if you read before exam, you're doing yourself a very, very huge favor. Just tell yourself that I'll do the hard work now. I'll finish it before first, second week of the semester resumption. Then once everything has resumed, once it has happened, you've covered the semester, the syllabus, I mean, and you will. Okay, so I'll be starting afresh. So I was trying to give a an introduction to what we are trying to do. So this is a 12-week lesson, meaning if you start with us right now, by 12 weeks time, you will be able to have completed your syllabus completely. And I always would advise students that they should try as much as possible to finish the syllabus as quick as possible, because doing it that way, you'll be able to buy time for yourself and you'll not really have to worry with the whole semester stress. That was one of my secrets while I was in school. Before the semester starts, I was that kind of person. Before the semester starts, I would finish the hard subjects, their syllabus before the semester starts. Then when the semester is on, I will joke with everybody, I'll play with everybody. I'll play games, people will be wondering how, but this is one of my secrets. So if even if you're a slow learner, it would help you very well. The earlier you start, the better for you. Yeah. So yeah, this is week one, and the topic for today is mechanics and properties of matter. Mechanics and properties of matter. So we'll be these are what we should be able to do at the end of this lesson. These are the objectives. By the end of this lesson, we should be able to define physical quantities and also perform different unit conversions. Also, we'll be able to master measurements of length, mass, and time. In addition to that, we'll also be able to apply dimensional analysis to verify physical equations. So all this grammar I'm speaking, by the end of this lesson, we'll come back and see if we really have grasped this stuff. So finally, we'll also be able to resolve and calculate vectors in Cartesian systems. So let's go into the lesson properly. So starting off, we will be looking at physical quantities and units. So first off, measurement is one of the things I think would help you. You first need to talk about measurement before you start talking about units, because when you measure, you would then need to measure with respect to a particular unit. So it's important that we know what measurement is first before trying to go into units. So measurement is the process of comparing an unknown physical quantity to a known fixed standard. And this fixed standard is what we now call units. So now we know that when someone says 1 dozen, we know what 1 dozen should mean. It should mean 12 pieces of a particular item. So it's like a standard. So that's the same way that we try using units to represent a particular measure of a particular thing. So as I have here, I said it is the process of comparing an unknown physical quantity to a known physical standard or to a known fixed standard. So we use there are different systems of units. There are different units. There are different units that they can use to attach to a particular measurement, so people would understand. So this without these units, it can be confusing to know what you are trying to measure. Just imagine I said it for me to come here, it took me 5. For me to come here, it took me 5. So what am I saying? Is it 5 meters or 5 seconds or 5 joules? Maybe I burnt 5 energy, 5 joules of energy. So if I don't mention the units, you will not really know exactly what I'm talking about. So 5 is something that can be applied to both time, can be applied to both temperature, it can be applied to anything. So by mentioning the units, it helps you to know what you are trying to measure or what you are trying to talk in respect to. So that's why units are important. They try to help you to define or clarify an unknown measurement. I don't know if I'm communicating. So now, if I said it took me 5 seconds to get here, people will know, okay, maybe you did not really spend much time. If I say it took me 5 kilometers to get to this place, like, wow, he came from a far distance. We know you're talking about because we're getting meter, it came from a far distance. If you say it took me 5 joules of energy, 5 joules to bring myself here, I'm still saying the same thing, but I'm adding different units. And because of these different units, it is meaning different things. So these units, they try to help us give a definition or to understand what the person that is talking or what the measurement is talking about. So systems of units now, as I said, there are different systems of units. So there are different systems. So these systems of units are just like I'll call them their standards, because I said units, they are like standards that they use to measure stuffs. They are standards that they use to measure stuff, known standards. So now there are different standards that people use to tag to a particular measurement. So we have the CGS system of units, we have the SI system of units, and we have several other systems of units. So the international system of units is what we know as the SI unit. So this one is one that currently, among scientists, they accept it worldwide, not just nationwide, worldwide. So meaning if you use this particular unit parameter, because this systems of units now, they can be several systems of units, several systems of units. So now, just imagine like the example I was trying to give, I think yesterday, just imagine you said something like, this thing is 5 inches long. Someone that is not already familiar with inches might be confused. How is 5 inches long? Someone that maybe is used to kilometers will be like, do you mean this is going to be long or five in what I know is 5 kilometers when you're talking about length, and 5 kilometers is a very long distance, but 5 inch on the end of inches is very small. So there will be a kind of confusion if there is no universally accepted system of units. So scientists came to a conclusion that they would use a defined or a unified system of units across the world. And this unified system of units is what we know as the international system of units, also known as the SI units. So it ensures that what we see, what we measure, what we use to measure length in Nigeria is the same thing as what they understand length to be in even the US or UK or Canada, wherever it is. So that anybody that says, okay, oh, it took me 300 meters to get here, someone in the abroad or someone abroad, someone outside Nigeria will be able to say, okay, okay, 300, I don't know 300 meters, I can measure it. So they can be able to tell, they can be able to communicate easily. So that's why this system of units are important. So for physics, basically, they most of the times would use and even advised to always use the international rather system of units. And this one is the units where mass is measured in kilogram, length is measured in meters, time is measured in second, kilogram, meters, second. So this is like the simplified form to always identify that, okay, this is the SI unit. It is typically always in kilogram, meters, second. Mass in kilogram, length in meters, time in second. There are other things that change. Are also Kelvin is also SI units. You can measure Kelvin in you can measure temperature in Celsius. You can measure temperature in Fahrenheit. You can measure temperature in Kelvin. But for the SI system of units, for the system of units international, it is Kelvin. So that's just how that's the purpose for this stuff. So now, aside this system of unit being the universally accepted system of unit now, if we then dig deeper into or look now specifically to these units now, some units could be a combination of two or more units, while some other units could be just the fundamental or the basic or the crudest of units, or let's say the building block of other units. So the ones that are building blocks of other units, let me say it like this. Assuming we are trying to look at a building, or we're trying to look at, let me see, my mind is just messing with me. Assuming we're trying to look at a building from bricks. No, bricks are okay. Looking at what are the basic components of a particular building, a building. Every building is always made up of sand, cement, water, then sometimes gravel. So these are the major components. Then sometimes maybe iron rods and all those stuffs. But these are like these ones that are the like the crude implements, the raw materials. Yeah, they are what are known as fundamental units or fundamental units in the terms of physics. We're talking about units. They are fundamental units. They don't have. If you go down below sand, what else can you call sand? Sand is sand. What they use to make up sand? They use sand to make up sand. So sand is like a base. If you're not trying to look at it in chemical aspects, just looking at it as what it is physically. Sand is sand because we're doing physics, we're not doing chemistry. Sand is sand. So sand being sand, it is the basic, the let's say the crudest of form that they use to make a building. Sand, cement also is the crudest of form of that element that they use to make a building. But now when you bring it together, you will see something like brick. They could mix some sands and some cement with water and you form brick. They could mix some sand and some other one, you can form mortar, and so on. So these ones that are mixtures, they are the ones that can be seen as the derived units. Derived means are the ones that are mixtures of the fundamental units. I don't know if I'm making sense. I don't know if I'm making sense. So we have jollof rice now. Jollof rice is made from rice and all the single ingredients. Those single ingredients, they can be seen as the fundamental units. But when you start merging them together, they are now forming two, they're now forming derived units. They are made from the fundamental ones. So I think that should drive something home. So examples of this hello, can you guys still hear me?
Yes, sir, we're hearing it.
Yes, sir.
So,
Yes, sir, we can hear you.
so now examples of these fundamental units, we have kilogram, we have seconds, we have meter, we have Kelvin, and so on. There are many of them. There are many of them. We have what they call it. There are several of them. There are moles. They are examples of fundamental units. So a mole is a mole. They did not join maybe time and something to make mole. Mole is a mole. You get, mole is a mole. Kilogram is the mass of something. They did not join something and something to make kilogram. It is the basicest of its form. I don't know. I'm trying to use English. I should probably show the intensity of what I mean. So kilogram is the crudest of form. Mass, I mean meter rather, is the lengthest of length. It is the smallest of like the lengthest of length. Let me use it that way. I believe you should get what I'm saying. Second is the secondest of second. So there is nothing that came together to bring up a second. A second is just a second. So now, when you now start joining meter and second together, you are forming something like meter per second or meter second and so on. Those ones now, they then become derived quantities. When you're having a merge of two fundamental quantities, it gives us derived quantities. So by definition, you can say fundamental quantities are quantities, or fundamental units are units that cannot be derived by from others, while derived units are the ones that are combinations of two or more fundamental units. I believe that should make sense. And we have our examples here. We see volume, we see density, we see speed, we see Newton, we see energy, we see pressure, and so on. So I don't know if anybody has any question for now. Does anyone have any question?
No.
Uh, um, Good evening, sir.
Yeah, I can hear you.
So I wanted to ask if, like this part in the physics, like this fundamental part and derived part, is it really important in the exam?
Yeah, yeah. It's important. As simple as it may seem, you would see questions that would come out from it. You'll be surprised. They could just imagine that they tell you, is Pascal a fundamental unit or a derived unit? If you don't know what
Yes.
Pascal is, you might be like, is it a fundamental? And you might not even know what it is. Or they might even tell you, Pascal, what are the elements that are used to make the derived quantity Pascal? Meter is involved,
Okay.
kilogram is involved, second is involved. So that's why these things are, it makes sense that you just first understand what the concept is talking about, then know how they come together. So I hope that answers your question.
Yes, sir. Thank you, sir.
Yeah, you're welcome. So now let's moving forward. So now normally probably you might see some other places where you should have seen it in your textbook where they will tell you volume. Volume is meter times meter, giving you meters cube. Density is what it is. Speed is what it is. So these ones I don't want to dwell on this because I know that you can find it in textbook. You will find it even in your notebook. You will find it everywhere. Fundamental and derived quantity. So it's of no need to really try to be emphasizing on these stuff because it's common knowledge. So that's why I think I'll be moving to the next slide, leaving this behind. So now moving forward, yeah. Did someone call me? Okay.
No,
So
sir.
someone's mic is turned on. Please, could you turn down your mic? Okay. So now moving forward to measurement tools. So there are different measurement tools. There are different measurement tools, and sometimes when I look at this topic, I'll be like, is it necessary? People supposed to know, but as much as it is common, there are still some points that are intricate. So there are several measurement tools. We have the measurement tools like that are used for measuring length. They are the ones that are used for measuring diameter, like the vernier caliper or the calipers. They are used to measure diameter, both internal diameter of hollow materials and external diameters of rounded materials. So there are two types of calipers. There are two types of calipers basically. There is a vernier caliper and um what's they call that stuff? There is a vernier caliper and the one that's used to measure internal caliper, the internal structures and the external structure. So there are two types of caliper. The one that is used to measure the outer radius of a particular thing, and those that are used to measure the internal radius of probably something like a pipe. So it's still a caliper. So we also have the micrometer screw gauge. We have all of them. There are many. There are many measuring, even meter rules and their likes. So these are tools that are used to measure length. Then mass and time. We know what we use to measure mass. Mass is measured by weighing balance and so on. Someone's mic is turned on, please.
Excuse me, sir.
Yeah, I can hear you.
Sir, please, the slide, it has not been sent to us on the group so that we can be following it.
Okay, let me see if I can leave the call. Let me see. As I was saying, we have different measuring tools, and they have their uses. They have their uses. So somebody might be asking, why do we need to know this stuff? Why do I need to know this stuff? Micrometer, screw gauge, they are a kind of instrument that are used to measure things, length. But now they're not just used to measure any kind of length. They are used to measure length in micrometer, hence their name. Vernier calipers, they are used to measure stuffs in stuff that are less than millimeter. So that's when you employ these kinds of instruments. So you don't use a ruler when you're trying to measure
Yes.
something that is very small. You can use a micrometer screw gauge to measure something that is very, very small. So that's why some of these things are important to know. So now, that being said, um, we have what is called scaling factors or units conversion. So now, when we have these different units, these units could be in one form or the other. We could probably have them in, let me say, we have a particular unit, maybe something like 4,000 meters. You could convert it to something that looks less heavy to the eye. 4,000 meters looks like, wow, that's large. But how about you say 4 meters? It looks a little bit easy to remember. Like you don't need to memorize how many zeros are there. So doing this kind of conversion while you are still maintaining the same unit is what they call unit conversion. Is when you're trying to scale up or scale down a particular measurement. When you're trying to scale up or scale down a particular measurement, you are doing unit conversion. So you're not trying to change the measurement to another thing. You're just trying to either scale it up or scale it down. So as me, you are trying to talk about from from meter to kilometer. You're trying to do something like a scale up, scaling from a small size to a larger size, or to a larger unit, from a smaller unit to a larger unit. So now if you are scaling down, you're trying to change from kilometers to meter. You're trying to scale down the unit. So it's not that you're reducing the size of the parameter or of the measurement. You're just trying to scale down the units. So that's why they call it unit conversion. You're not converting the measurement. It's unit conversion. So you're just changing the units from one scale to another scale. So let's see what we have here. I said think of units conversion like scaling a recipe. If a recipe of two people uses 500 grams of flour, but you have 10 people, you convert the units of 7 to total grams in physics. We use conversion factor, blah 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 blah. So all these things now, these scales, yeah, the place where this advantage of this scaling or of this unit conversion will come into play is when probably you are trying to achieve something, but now you have limited resources, but it is something that is sensitive, something that is measurement sensitive. So you can say, okay, maybe they said normally to prepare a meat pie, just one meat pie, you need maybe, I'm just assuming, I'm not a baker or a chef. Maybe they'll tell you need like 2 grams of flour and 1 gram of no 2 grams of flour and 0.5 gram of sugar. Then you'll be like, that's for this one. I want to now get something more than this. I want to do more than one meat pie. You then say, okay, oh, meat pie, they don't use sugar in meat pie. Jesus, sorry about that. So just assume I'm not a baker. So you then need to scale it up by saying, okay, if one can give this, you can then convert that unit and say, okay, oh, if I have more of this, it should be able to give me something like this or something related to this. If one can give this, something, this other one can give this. So we are doing something like unit conversion and scaling. Unit conversion and scaling. So now these units now, when you're moving from different scales, from kilometer to meter, we know that story or that all those songs that they sing when we were in primary school. Somebody at this point might be like, why is this an importance? Why are they stressing us early in the morning? We will come to school. They will now start teaching us stand with skin on the board and be knocking the board and say 10 centimeter make 1 decimeter. Then like just continuously repeating song that's it's not really interesting. But now if you memorize those things those times, it should make sense to you in your present time. All these things they build on themselves. So when you can be able to know the amount of a particular unit scale that is equal to another measurement in another scale, like we know now that 1,000 meter is equal to 1 kilometer. So that 1,000 now is the conversion factor to move from meter to kilometer. 1,000 is the conversion factor to move from meter to kilometer. So by knowing this thing now, you can now scale from meter to kilometer by using the conversion factor. So if 1,000 meter is equal to 1,000 meter is equal to 1 kilometer, that means 5,000 meters will be equal to 5 kilometers. So we've done a scale up. We've scaled up this particular measurement to see how many will be required or what to be the representation in something larger. So I hope it's making sense. So that being said, we will then be moving to dimension. We've talked about units. We've been talking about units. So now we are leaving units now and we're trying to go into dimension. So what is even the difference between units and dimension? So I would say the simple definition is that unit is that thing that they use to measure, but dimension is like what would I use to simplify this? Dimension is what determines the unit. Dimension is what determines units. So we have some major dimensions, and these major dimensions we have are mass, length, and time. Mass, length, and time. So its mass is the measurement that gives rise to the unit kilogram. Mass is what you're trying to is the dimension you're trying to measure that will give rise to the unit kilogram. Length is the dimension you're trying to get the unit meter. Time is the dimension you're trying to get to represent the unit as second. So the units are used to represent dimensions or different measures of dimensions. Units are used to represent different measures of dimension. So these three I mentioned, they are like the major, I would say that they are like the major dimensions when it comes to physics. There are several others, but they are not really popular. When you're trying to talk about mole is just n. The dimension for mole is n. So there's nothing you're not really trying to convert. It's just that's what it is. So the dimension m, it represents the quantity of matter, and the dimension is denoted by a capital letter M. The same thing for length. Length is to represent distance or displacement, and the dimension is denoted by the capital letter L. Time is represented by capital letter T. So let's see how these dimensions they come to play. As I said, dimensions are what predicts what units you would use. So now, assuming you were given a particular expression, assuming you're given a particular expression and you're trying to get the unit of that expression, the easiest way to get the unit is first by getting the dimension. Then once you've gotten the dimension, you can then convert the dimension to get the units. Get the dimension, then from the dimension get the units. But in case you were not given the dimension and you were given, the units, you can use the same units to get the dimension. So it's a two-way process. You can use the units to get the dimension. So now also you can also use dimensions of the ones you know to get a particular the dimension of an unknown parameter or an unknown measurement in an equation. You can use the dimensions you know to get a dimension you don't know in an expression. So now let's see an example of something like that. I think this is a typical past question, how it comes out. So they will give you an equation and they will tell you, okay, oh, this is an equation. We don't know the dimension of something. This is a typical question. So it's the kind that you would always almost see. They will give you an expression and say, this is a particular measurement. Oh, these are the dimensions, but there is one that we don't know the dimension. Find the dimension or the unit of that particular measurement. They could ask you to look for the dimension. They could ask you to look for the mean unit. So now, to do that now, you will first need to take each of the parameter in that equation, one after the other. Each of them one after the other, and get their units if you have the units already, or if you are given the units, or if you know the units. Use the parameters, get their units. We know G is acceleration due to gravity, right? So G being acceleration due to gravity, G is equal acceleration due to gravity. Acceleration, if you are conversant with it already, acceleration is measured in meters per second square. So you can write it on one portion of your notes. G is equal to meters/second raised power 2. K is what they asked us to look for. They say find the dimension of K. We don't know K. K is equal to question mark. R is equal to radius, and radius is measured in meters. So you write R is equal to M. Sorry, what am I doing? Then this one that looks like P is density. Is density. Density is measured as mass over volume. Density is measured as mass over volume. So mass over volume is kilogram per meter cube. Kilogram per meter cube. That is kg slash m raised to power 3. Write it down. So if you've been writing what I've been explaining, you will know that you now have the units for each of these parameters. But they asked us to find the dimension. So now from this unit, we can now get the dimension. So now we have the units for gram, for G, which is meters per second. Meter is a measure of length. So you change your meter, your M, your small letter M to L. Second is time. Change your S to T. So you should be having in your, where you have your G is equal to M slash S raised to power 2. You cannot write equal to L slash T raised to power 2. Replacing M with L, replacing S with T. Do the same thing with radius. Replacing M with L, you would have your R to be equal to M and also equal to L. When you then go to the density is equal to mass over volume. That's M over V raised to power 3. Sorry, kilogram. I mean, what am I saying? Kilogram slash M raised to power 3. So kilogram slash M raised to power 3. Kilogram is for mass. So you put kg as M. Sorry. Can you guys still hear me? Hello, can anybody still hear me?
Yes, sir.
Okay.
Yes,
So,
sir.
okay, thank you. So kilogram kg is equal to M slash L raised to power 3. So that way we already have our dimensions for the ones we know. So now when we now have an expression like this, so this is now where importance come to play. When you have units or when you have measurements that are separated by plus or minus, it means that both of them are equal. They have the same dimension and they should have the same units. They should have the same dimension. Let me use the word dimension. So they might not have exactly the same unit, but if you multiply their units together, it will give you exactly the same dimension. So when different parameters are separated by plus or minus, the two by their side that are side by side, they are equal. They have the same dimension. But when they are not separated by minus, when they are joined together by multiplication sign, it means you will not need to separate their dimension. You multiply their dimension to get the overall dimension. So see here we have G on this side here. Here we have KRP. So now the entire dimension of this place here, of this your right hand side, should be equal to the entire dimension on the left hand side. That's one of the rules for dimension. Dimension for left hand side should be equal to dimension on the right hand side. When they are talking about an equal to, it should be always equal to the one on the left hand side and right hand side. So now we are not looking for G. We know that the dimension for G is L T raised to power minus 2 or L slash T raised to power 2. But now this one here, now we don't know K own. So to get a simplified representation, we know G, we know R, we know rho. That is one for density. So let's first rearrange this expression to make K the subject of formula. So by rearranging that, we'll be having something like this here. K is equal to G over RP. So we already have the dimensions of G, we have the dimension of R, we have the dimension of P. So now we will now replace those dimensions in this expression. G's dimension is this here. R's dimension is L here. Rho's dimension is this ML or M slash L raised to power 3. So if we put it together in a mathematical expression and we simplify it, cancelling M for M, L for L, the ones that are up, divide the ones that are down, and so on, it should be simple math, or use indical expressions using indices and plus the multiplication and subtraction, multiplication and division of indices. If you use that rule, you'll be able to get a simplified expression of the dimension, and that simplified expression is what is now going to be known as our dimension for K. That is how we used to get dimension from known to unknown. From known to unknown. I don't know if anybody has any misunderstanding from what I explained so far.
No, sir.
Okay.
No, sir.
Anybody doesn't? Okay, so meaning we can move forward, right? Yes, so let's
Yes, sir.
go forward. Let's go forward. So it's that simple. Once you can be able to move from what you know, getting dimension, you can get the one you don't know by using normal algebra. So now there are some units or some measurements that they look they look alike. They seem very much alike, but they are differentiated by some kind of key stuffs. Like sometimes some people don't really know the difference between mass and weight. If I say something has a mass of 50 grams, somebody will be like, oh, 50 gram, I know what 50 gram is. That means that is the weight. Now, actually, that is the weight. Gram is different, mass is different from weight. Mass is different from weight. Mass is different from weight. Mass is just ordinary the mass, the composition of a particular entity. The composition of a particular entity in a unit known as gram. But now when you're talking about weight, it is the composition of that entity multiplied by the force of gravity or the acceleration due to gravity. So when you're talking about weight, you are including gravity to the equation. That's what we have here. Say weight is equal to mass times acceleration due to gravity. While here mass is just equal to gram or kilogram. So mass, when you're talking about mass, you're just talking about the composition, everything that makes up that particular entity. Like our mass now, most of us know our weight, but we don't know our mass. So we can get our mass by looking at our weight and using acceleration due to gravity to divide our weight. We can be able to tell our mass. We can be able to tell our mass. So mass is different from weight. It can be tricky, but just know that they are not the same thing. The amount of matter in an object is what is the mass. The amount of matter or the amount of particles, not really particles per se, but the amount of matter, both solid matter, liquid matter, gaseous matter, the amount of those things that come together in a particular object is what is known as the mass of that object. And the mass of an object is always constant everywhere in the universe. So your mass here on Earth and your mass in space is exactly going to be the same thing. But your weight in space is zero. Your weight in space is zero because in the space there is no gravity. So your weight in space is zero, but your mass is always the same thing. As mean you checked your mass now from the formula I told you guys. As mean your mass is 100 grams. If you go to space, you will still have a mass of 100 grams, but you have a weight of zero. But when you are here on Earth, you probably would have a different weight. You will have a weight, definitely you have a weight because gravity will by then that time start acting on you. So that is the difference. So when you have the addition of gravitational force to the mass of an object or the multiplication of gravitational force to the mass of an object, you are talking about the weight. I hope that is clear. I hope that is clear.
Yes, sir.
Okay, good.
Yes, sir.
So now let's see error analysis. Error analysis. So I don't know how many of you were in the lesson yesterday. How many of you attended chemistry lesson yesterday?
Good evening, sir.
If you attended, just
Hi.
say hi.
Yes, sir. Hi.
Okay. So without looking at what we have here on my screen, as I could cover my screen, I've covered what we have at this end. I would have asked you guys what is random error and what is systematic error based on what I explained yesterday. So from what I explained yesterday, yeah, someone should talk. Let me listen.
Good evening, sir.
Yeah, good evening. Can someone help us? From
Good
what?
evening, sir.
Yeah, good
Sir, please,
evening.
I have
Based
a
on what we
question
explained,
concerning that G equals to K.
yeah, someone should.
Yes, that example.
You said
K.
okay. The previous example. Okay, see it here.
Yes, sir.
What's wrong with it? Do you want to screenshot it?
No, sir. I have a question concerning it. You said that we have to find, the question says we have to find the dimension of the constant
Of
K.
K. Yes.
So the thing is that when I was taught in class, we
Yeah.
be given the the name. I don't know, but I feel like it's supposed to be equals. Like for example, oh God, I don't know how to explain it, but I feel like there's supposed to be
I didn't
like
really get it. You
a
say you feel
unit
like
for
what?
K
Your network.
to get the dimension of it or something like that.
Or there you go.
Okay, the dimension.
But my network is
Yes,
slow.
it happens sometimes. Sometimes.
Okay,
Sometimes.
sir, can you hear me now?
Somebody was explaining, saying that sometimes that they're supposed to give you the unit of K. So I was saying, if they gave you the unit of K, it's simple then. With units, you would easily get dimension. With
Yes,
units,
sir.
you would easily get dimension. So now, in case you are not giving the unit and you are giving something like this now, you know that you know the unit. This is G, and G is acceleration due to gravity. So you're supposed to know that one from the back of your mind. That is meters per second square. So
Yes,
R is radius, is meters. This one that looks like
sir.
P rho, it is kilogram per meter cube. So just first off, use this expression, make K the subject of formula. Then from the units of these ones, of G, R, and that P, simplify their units or bring them together in the expression. That is the expression of this. This one you have here, G, R, P. Put their units together, cancel the one that's supposed to cancel. Use meter to cancel any excess meter. Use kilograms, cancel any excess kilogram. Use seconds, cancel any excess second. You will now have a very simplified one. Then those units that you've gotten are the most simplified units you've gotten. Just represent them in forms of their dimension, and you've gotten your answer.
Oh,
So,
I understand. Thank you.
so that, so that's it.
Thank you.
So that's it. Okay. So we can move forward now.
Yes, sir. Sir.
Okay. So let's move forward. Yeah. So I was saying the previous day we had random errors and systematic errors, and I was trying to ask people that were present yesterday to try based on the example I explained yesterday, because I think I use examples and I use examples that we can remember. Based on that, what can you say about random error and systematic error aside what you are seeing on the screen now?
Systematic error, you said that there are consistent, predictable errors that are usually caused by faulty equipment or poor design. And you used, example, a filling station example where you go to fetch there, let me say, for one liter, and you're always going home with 0.5, and then someone meets you and be like, this filling station, their machine is faulty, something like that.
Yeah, exactly. Thank you so much. Thank you so much for this. At least it means you guys were actually paying attention. I'm really grateful for this. Thank you. So yeah, systematic errors, they are predictable. They are very predictable because it is mostly caused by the machine. So they are consistent and they are predictable. What do I mean by they are consistent and predictable? Let me use back the example I used yesterday so that it would make more sense what he was trying to explain. Assuming we went to a filling
Sir.
station and yeah, someone is calling me. Hello.
Yes, sir. Sir, I have something to say.
Okay, I'm listening.
Sir, can you please I have something to say, sir?
I'm listening. I'm
Okay,
listening. You can
so
go on.
to my understanding, I feel like systematic. Okay, sir. So to my own understanding, I feel like systematic errors are errors that can be determined. While random errors are errors that cannot be determined.
Okay, yeah, it makes sense. That it makes sense too because when you use the word predictable, yeah, you can determine what it is. So that's still correct. That's still very correct. So they can be determined. The other ones they cannot be easily determined. You cannot tell that this error would happen. So predictable is I would I say is the better word for it because predictable means you can tell the error. While when it is not predictable, yes, you cannot determine it, but you cannot really tell whether there will be an error or there will not be an error. So you cannot predict whether this particular measurement I'm making there is an error in it. But if there is an error that is a systematic error now, you can be able to easily say, okay, oh, If this error is here, it means that the remaining 5 measurements I made, this particular same measure of error would still be replicated throughout all of them. So without even going to go and check each of them individually. So assuming you went to a filling station, as I was trying to explain, and the filling station, they say 1 liter, 1,000 naira. But now they will pump 1 liter for you and you check it. It's not up to 1 liter, it's 0.5 liters. If you bought 10 liters, you can tell that each of the liter short by 0.5. So meaning that your 10 liter now, instead of it to be 10 liter, it will be 5 liters that is inside your gallon. So that way you can, from the fact that you can know that, okay, there's a 0.5 liter error in this system, it means that everything I've been buying from these people, there's a shortage of 0.5. So it is easy to predict. You can predict the error. But now, assuming it is the error was caused by the person that was pressing the machine, not the machine now, because that one is the error that is done in the calibration of the machine. The 0.5 is for the machine. So now, assuming the person that was pressing the fuel, that means pressing is, then the machine is not showing that its number. And you say, I want to buy 5 liter. Well, hey, let's say we go to no, that's not an example. The machine, let's assume that number is not showing very well, or the number is not showing. The person pump, the person say he pressed the number 10, 10, 10. The person press the same 10 liters for you, but he's pumping it. The person now stop and say it has finished, it has stopped. You know, be like, you sure say you don't finish? Say yes, I don't put that for you. Person lock his machine. You don't know how many shortage you've gotten. You don't know whether the thing was just remaining 0.5 liters complete, or whether the person even pumped the entire distance. So it is unpredictable because it's an error that was caused from the man that is doing it. It's not the machine that has the error. So you cannot even tell how many degree of error was there, except you can measure it. So if the man pumped somebody's own before you, he might have stopped the person's own. Let's say the person wanted to buy 10 liter. Might stop the person's own at 9 liter. Stop your own at 8.5 liter. Stop the next person at 9.5 liter because he's not measuring it with his head. He's just measuring anything that he feels, okay, this one should be okay. He will do, oh yeah, go, you go, you go. So those kind of errors are not predictable, and the errors that are called random errors. So they are not predictable. We cannot predict what they are. So I hope that is clear now. I
Yes,
hope you
sir.
guys can hear me.
Yes, sir.
Okay, very good. Yeah, so now, looking at here now, I've talked
Yes,
about
sir.
this. They have the same explanation.
Yes, sir.
They have the same explanation: systematic error and random error. So now, significant figure, as I was trying to explain also yesterday, I said they are used to adjust a particular value, a large value, to simplify it to form simple, like a simple expression of large values. So from what I have here, I said this significant figure, they define the precision of our results. And sometimes they can when the significant figures, we can use significant figures to predict what the error will probably be. Because let's say we had a measurement, and that measurement was say 5.81888, and we rounded it off to 2 decimal place. We'll be having 5.82. So now, yes, it's close to the answer, but it's not the exact final answer. It is not precise, but it is close. So we can say the precision between it and the original answer is, we can measure it by subtracting the original answer from the adjusted answer. So that way we can calculate the error. So that approximation to significant figure, it can help you to tell how precise your answer is. It can help you tell how precise your answer is. So if it is exact, you know that your answer is correct. But if there's a deviation, if there's a kind of error, a little, even if it's 0.001, you can answer that, okay, your answer is not accurate, but it can be precise. I remember yesterday I was trying to explain and differentiate between accurate and precise. Accurate means that it is the exact value, it hits the exact target. But now precise means it's close to, or what you are measuring, they are close to themselves. I don't think it's here on this slide, so I will not really need to go into that. I'm drawing us back into something that is not here on our slide. So now let's move on to graphical analysis. So I remember when I was in while I was in my secondary school, graphs were somehow annoying to me because I was like, I don't understand. They will not really tell us what to do. They just tell you on this side, see this side, write graph of 3 centimeter equals to 7 units. I'll be wondering what's the meaning of that one. I don't really understand. I'll just write. They will tell you, write the title of the graph. The graph is a graph of so and so again, so and so, or so and so on the x-axis again, so and so on the y-axis. You don't really understand that stuff. But graph, later when I got to understand how graphs work, I tend to love graphs very well because they can help you to easily visualize the relationship between numbers. Can help you visualize easily the relationship between numbers. So what do we have here? I said in physics, we basically use straight lines in physics. We basically, when we plot graphs in physics, we always try to use straight lines. There are times where they use curve, but basically they would always try to use straight lines. And that's where you now start seeing line of best fit, where they will try to adjust the straight line so that it will try to be closest to all the readings that you measured. So these graphs now, the place that is always looking like as if it's pointing to heaven when you are looking at your book, the line that looks as if it's pointing to heaven, that line is your y-axis. Why the one that looks like as if it is on your table? That one is, I mean, what I call it, looking at heaven. The one that looks as if it is going up is y-axis. The one that looks as if it's going to your side is the x-axis. I'm saying this so that in case of people that are not already conversant with what they are, I'm just trying to make it so that you'll be able to get a picture of what it is. Everywhere, your y-axis is always like this. Everywhere, every graph, your y-axis is always like this. And your x-axis is always like this. So now, when you plot graphs in physics, you will always try to plot straight line graphs. And those straight line graphs, they are known as lines of best fit. They are like an approximation of they are like a kind of approximation of the reading, the entire reading you got. And most of the time, the slope of those graphs can show you the prediction of what the straight line should be. Or the slope of that straight line can be used to predict future values. That's the better word. The slope of a straight line graph. Why they prefer using straight line graph is because physics, most of the time, they always try to assume. So now, why do we use graph? We try to use graph to predict values that are not on your chart or on your table. So now let's assume we tried calculating the slope of a particular graph and we've gotten the slope of a particular graph. We can always put that slope of a graph to the equation of a line. Since when I learned this thing, it made this graph stuff very, very interesting to me because anything you can plot a graph of, you can predict its future. So if as mean you've been selling, let's assume you are a business person and you take note of your records. Take note of your records, and maybe you record it number of sales per day for the entire year. If you can find a straight line, or if you plot on a graph and you can find a straight line, you can predict what or when your next high sale should be, or when your next low sale should be, depending on how the thing is seeing the relationship, how the graph is. So the graph can give you a straight line graph. If the graph can give you a straight line, whether it's a negatively sloping straight line or a positively sloping straight line, you can predict the future once you can get the slope of that line. So when I was saying positively sloping is when it's going from down up, not this way. I'm not saying this way. I'm not saying down up from your left to right, from your right to left, down from the way you're writing on your book, down from where you're writing in your book to the other side as you write. When you're writing, you write from your left to your right. So when it is moving from down on your left upwards to the right, it's a positively sloping graph. When it is moving downwards from your left to your right, downwards from your left to your right, it's a negatively sloping graph. So just take note of these things. These two things would help you. So when you have a negatively sloping graph, you would have a negative slope, as the word implies, negatively sloping graph to give you a negative slope. When you have a positively sloping graph, you should get a positive slope. You should. So this expression that we're seeing as y equals to mx plus c. Y is always used to represent the things on the y-axis, what you're trying to predict on the y-axis. X is talking about what you're trying to predict on the x-axis. Then m is the slope or the gradient, while c is the intercept. And intercept represents where the straight line touch on the y-axis. So if the straight line touch 0, it means that the intercept is 0. If it touch -1, it means that the intercept is -1. If it touch +1, it means that the intercept is +1. So that's what these things mean. Y represents y-axis, x represents x-axis, m represents the slope, while c represents the intercept. So how is this important? I was saying that you could use this thing to predict your sales or what your next high sale should be. So how does this happen? let's assume your sales, you are selling, this is your, or let's assume you have been tracking the price of something, maybe the price of say the price of Milo from years ago, and you found a graph that is like this, that is sloping like this, that the price of Milo has always been going up like this. You can predict to a reasonable level of probability that, okay, well, since the price of this thing has been going like this, and today is this now, we know that the price of this thing is like this. You can now say, okay, if today is, let's say today is Monday, tomorrow is Tuesday, and maybe the number, the date, you see the date here, or let's say, let me use numbers. The number here, if you take that number here and put it into X, because this is your X axis, you can tell what your value on the Y axis will be, because if you have your slope, you can just put X as what it is, put slope as what it is, and you get the intercept, the thing touch where it touch on the Y axis. If you can get that, just put into the equation, you will get your Y axis without even it being on the chart. You can get what will be on your Y axis. So I don't know. This is something I would have liked to do with more, would I say, a graphics tablet, so that we can be able to see examples of this. But I just hope we probably get a little bit view of what I'm talking about. So these graphs now, they are used to predict, and I've explained what the graphs are basically comprising of, what the equation of a line for graphs are basically for. So you plot several graphs in physics, especially if you are doing physical sciences or any of the physical science or even engineering. You would plot graphs. You would plot graph, even chemistry aspects, physical sciences, as I said, you would plot graph. Math, so you plot graph. So you don't need to be scared of graphs. You just need to understand the idea of graph. So this is for straight line graphs. Curved graphs, they also have their own expression and their own equation. So, but for here, we're talking about straight line graph. So that being said, we'll be moving next to vectors. Vectors. I don't know if anybody has any question from what we've been discussing so far. Any question from what we've been discussing so far? Or can you guys still hear me?
Yes, I can.
I don't know if it's part of what you just taught us. I have a problem in picking slope. I say slope. In picking scale.
Okay, scale.
Yes, sir.
Okay. So scale now, it's if you can be able to look at your reading, you can be able to look at your reading. Let's assume you have your reading, they have value. Look for the lowest of your reading and look for the highest of your reading. If you can find the lowest of your reading and the highest of your reading, try dividing it by, like, let's assume you have your lowest reading is maybe 60, your highest reading is like 600. See the difference between each of them, 60 to 600. Try to subtract it, 60 from 600, how many it is, then divide it by the number of lines that your x-axis would have. That means your x-axis will contain 10. So 60 minus 600 is around, or let me use 100 to 600. 100 to 600. Your lowest value is 100. The highest value is 600. You now say, okay, 600 to 100. How many gap is that? That is 500. So 500 divided by 10 is how many? Is 50. So means if you put it 50, 50, 50, starting from 50 as the starting point. Don't use 0 as the starting point. Use 50 as the starting point. 50, after 50 you have 100, after 100 you have 150. Before you know, you will complete the entire thing and all your values would be inside, all your x-axis value will be able to fall in that your scale for that line. So now, because you use 50, it will mean that, depending on how you measure it, if it is those big box, it means that 2 centimeter, or is that big box is usually 1 centimeter. 1 centimeter represents, or if it is 2 centimeter, it represents, I think it is, let me see, it represents 1 centimeter. It means 1 centimeter represents 50 units. That thing that it gave you when you divided is what your centimeter, what 1 centimeter should represent. So 1 centimeter, you cannot say 1 centimeter represents 50 units. That's just how simple it is. So as mean your minimum value was 2, and your maximum value was, let's say, 20. 2 minus 20 is 18, right? So divide 18 by 10. So 1.8 is it here? So you can, instead of using 1.8, because 1.8 is an approximation, you can use 1.8. That is 1 centimeter represent 1.8 units, but you can now approximate it to the nearest whole number, make it 2. So you can now say 2 centimeter or 1 centimeter. I don't know, that seems like it's 2 centimeter. So whether it's 2 centimeter or 1 centimeter, I cannot really remember exactly. I'll need to look at the graph again. So if it's 1 centimeter, you can say 1 centimeter represents 2 units, because when you divide it, it gave you 2. So that way, when you now start writing 2 plus 2, 4. 4 plus 4, 6, 8. By the time you reach the end, it will be able to complete every single span of your lowest to maximum unit. You get? So once you can do it that way, you will be able to, both on your x-axis and your y-axis, get a skill that would match true. So that's like a simple hack. Like a simple hack. I don't know if
Thank
that
you,
makes
sir.
sense. Yeah, you're
Yes, sir.
welcome. So now let's move on to vectors. Let's move on to vectors. So now, vectors. I'll say this is one topic that sometimes it could be confusing. It can be confusing, but it's actually interesting. Though it's more complex than we would know in the basic level. That's advanced level. When you go into, if you are probably a programmer, not just a programmer, an artificial intelligence programmer, maybe someone that is into maybe machine learning or something like that. For those people that will probably branch into the other direction, you would tend to be very used to vectors because in those aspects, in machine learning and all those stuff, they are conversant with the higher level of vectors. So, but on the basic level, vectors are just talking about points and the direction that they follow. Points and their direction. Points on a particular graph and the direction which the point is moving towards. Points and direction. So that's why we say vector quantities are quantities that have magnitude and a direction. So a particular entity, a particular point, and a direction. So once you are giving a direction to a point, you are making a vector out of that point. Once you give a direction to a point, whether you say the direction is caused by a force or caused by whatsoever, so long as you are giving the direction a force or you are giving the point a direction, you are making a vector. So that is one of the simplest way I think I can use to explain what vectors are. So vectors are entities that have magnitude and direction. They are entities that have magnitude and direction, and there are different ways to calculate vectors. So when you have more than one vector, you could add these vectors or you could subtract these vectors. So you could add these vectors or subtract these vectors. There's some rules that they call the addition and subtraction of vectors. So for the addition of vectors, it is known as the parallelogram law. So it is used when two vectors act act at a point simultaneously. When you have two things acting at a point, like here, if you look at this point here, we have this is a point here. Sorry, this is a point here, and we have a vector acting in this direction. This is a point and an arrow. That's a vector. Another the same point, another arrow. That is another vector. Another point here, another arrow here. That's another vector. So we have three vectors here. So we can get the summation of these vectors, either addition or subtraction of these vectors. So, but for subtraction of vectors, it is the equivalent to adding a vector in the opposite direction. So, as mean when we are doing additions now, when the vectors are moving in the same direction, you would add these vectors, or their resultant can be equal to the summation of these two vectors. But when the vectors are moving in the opposite direction, their resultant will be gotten by subtraction of these vectors because they would cancel out themselves depending on which one is stronger. Just like as if anything you add direction to, you are making a vector out of it, even force. So if you are pushing a table forward and somebody is pushing a table backward, what will determine the resultant direction of the table that the table will move in is depending on who is stronger. So if the person at the front is stronger than the person at the back, the table would move towards the direction that the person in the front is pushing it. So it has cancelled the force of the person that is pushing it forward and overcome it and start moving in the direction of that the person that is in front is pushing it. So that is how subtraction of vector works. So when two vectors are in opposite direction, they would cancel out. Then anything that is remaining would then determine the new vector's direction. So, but when they are in the same direction, both of them will come together and become force, like the same force. Let's assume we have one person pushing a car, another person adds to push a car. The car would move with the energy of the two people, with the force and direction of the two people pushing it in the same direction. So that's how vectors are. So when you are adding vectors, you are using the parallelogram law. When you are subtracting vectors, you are using the vector subtraction method. So now, vectors, they are usually given in terms of coordinates. When you hear a vector, let's say there's a vector A, it always has coordinates. So it always has, what I mean by coordinates is that it always has y-axis, x-axis, and sometimes z-axis. y-axis, x-axis, and z-axis, which can also be repeated as I-axis, j-axis, and k-axis, or k component, I components, j component, and k components. So x, y, and z is when you're talking about vectors in terms of graph. But when you're talking about them in terms of components, just using components, you will call it I, j, and k. So I'm just telling you things that you will hear as you're talking about vectors, because you're just introducing vectors. So every vector has a component, whether just one, whether it's just an I component, or it has an I and j component, or it has an I and j and k component. In advanced level, you can even see several other components of a particular vector. So it's not only the x and y and z axis that we have. We have multiple axes, but that's just not for your level yet. So for your level, you just know that there are three axes basically, x, y, and z, or I, j, and k components. So when you have these vectors, you can add them using normal algebra. So let's assume you had a vector a being equal to 2i plus 3k, sorry, 2i plus 3j, and you have another vector a which is 1i plus 1j, and they say these two vectors are moving in the same direction. Find the summation of these vectors. It's just to add I plus I, add j plus j, and whatsoever it gives you, that's the final answer for the summation of these vectors. So it's just like normal math. It's not complex. When you're doing the subtraction, it's just like as though you can do the subtraction in two ways. By multiplying, let's assume you're doing a minus b. The first way to do it is just, okay, b is one that minus is in front of it. A is on its own. There's no minus in front of it. So there's no minus at its back. I don't know whether I'll call that in back or the front. But anyone, you understand what I'm talking about. A is here. Before A and before B, you have I. Sorry. Before B, you have I. That's A minus B. Before B, you have I. So that minus that is before B, you use to multiply everything inside B. So if B is I is 1I plus 1J, that minus will now multiply everything inside B, which is going to make it minus 1I minus 1J. So that way, once you've done that, once you've multiplied through, multiply B with minus, you can then add, forget that there's a minus sign, you can then add normally like as if it is a normal vector addition. So I think this is the easiest way to do subtraction of vectors. Just look at B and multiply B, the entire elements or the entire components of B, by minus. Then add A and B normally, or A and the result, the B, that is the minus B. I don't know if I'm communicating at all. I don't know if I'm confusing people, but I just hope that I'm not speaking jargon. So does anybody understand what I'm trying to explain, or is anybody confused?
A little bit confused.
He said?
A little bit confused.
Just a little bit confused.
Okay, let me say. Okay, I would like you guys to write this thing on your notes. Just write. I'll be calling it out from my head while you'll be writing it on your notes. So assuming we had a vector A equal to 2I plus 5j. Vector A is equal to 2I plus 5j, and vector B is equal to 3I plus 6j. Vector B is 3I plus 6j. If you were told to get the addition of this vector, that is A plus B. If you're told to add A plus B, it is just going to be simple. Add the two that are I, 3 plus 2, that is 2 plus 3 for the I side. Add them together, it will give us 5I. The J side, I've forgotten what was on the J side. I think it's 5 and 6. But what you have on your J side, add them together. You'll be having a resultant vector of 5I plus maybe something like, I don't know, maybe 11J. So if you've gotten that, that means that is the summation of the two vectors A plus B. That's the answer for A plus B. That's addition. But now when you have subtraction, maybe you have A minus B. So A minus B is the same thing as A plus bracket open minus B. True or false? So if A plus B, if A minus B is the same as A plus minus B, or A plus bracket open minus B, then what we will do is to first find minus B. So to get minus B, it means you multiply everything in B by minus. So B minus will now be equal to minus 3I. That is B minus will now be equal to minus, that is minus B is equal to minus 3I minus 6j. So our minus b is minus 3i minus 6j. So now if we're now to get the subtraction of these two vectors, which is a minus b, we said that a minus b, you can now write that a minus b is equal to a plus bracket open minus b bracket close. So then we already have our minus b to be equal to 6 minus 6i minus 3i minus 6j. So with that one now, you can then now add them normally. Add normal a that you have as your 2 plus 5, your 2i plus 5j, plus what you have as your minus b. You add it together and do normal math. I plus 2i plus minus 3i. Then just, you should be able to see it very well on your book, because I'm not really using a book now. So if you are writing it on your book, you should be able to see what it's supposed to give you, or you could punch it in your calculator. 2 minus 3i, it will give you an answer. 5 minus 6j, it will give you an answer, and that's going to be your answer for your a minus b. I don't know if it's clearer now.
Yes, sir.
Are you sure it's clear?
Yes, sir.
Okay, I hope it is, because I'm not ready with a graphics tablet to show or to illustrate on my screen. Maybe next time I'll be having the examples written on the board, on my slide. So now, vectors now, as we said, vectors could be in they have I and j components with k components. We can now have a particular vector and resolve it with respect to a particular component. That is to simplify a vector and make it in terms of a particular component. So, or to represent it in terms of a particular component. So now when we are trying to resolve a vector into components, we can resolve a vector into I components or the x component. Remember I said x and I is the same thing. Or you can resolve the vector into its j components or y components. J and y, they are the same thing. So the formula for resolving vectors into x components is, you would take that vector and multiply it by cos theta. Take that vector and multiply it by cos theta. While the j component of a particular vector, sorry, the j component, yes, or the y component of that vector is by taking that vector and multiply it by sine theta. So theta is the angle. Most of the time they will give you the angle in the question. Then you could just do your normal math, multiply the vector by the angle. So sometimes they will give you the vector value as a normal digit. So depending on what you are given, you will get your what they call it, your vector in terms of their components. So let me see whether we have an example forward. Okay, so here we have our example. They say calculate a plus b times c. A plus b times c. So we talked about vector addition and vector subtraction, but we've not talked about vector multiplication. So there are two types of vector multiplications. Before we start doing the example, there are two types of vector multiplication. We have the let me see, we have the time is going on. Let me see. Okay, thank God. So we have two types of vector multiplication. We have the the dot product and the cross product. So how you tell whether you are doing dot product or cross product for a particular vector? You will see when it's dot product, it's going to be something like this. When it is cross product, you'll be having something like this, something like that. So now there is a formula for that. So the formula is this for dot product, while the formula is this for cross product. So now take note, when you do the dot product of a particular vector, it would always give you a scalar quantity. That means what to give you would have magnitude but no direction. So have magnitude but no direction. But when you do the cross product, it will give you magnitude and direction. So this is just by default. You should just know this on your it because it could come out in an exam. They could say the product of they could say a plus this, or a cross b should give you what kind of what kind of quantity. a scalar quantity, a vector quantity, a magnitude quantity, and English quantity. You should know when you see cross products, you should know that it should give you a vector, that is a vector quantity. When you see dots, you should know that it should give you a scalar quantity. So these are important things that I was trying to highlight while I was preparing this note. So just take note of it that scalar quantities or dot product gives scalar quantities, while cross product gives vector quantities. So let's see an example of how these things they come in play. So here we have A plus B dot C. So there's a dot product that is happening here. So we'll see how the results will be. So A plus B. To do A plus B now, we'll be doing normal A plus B as we said it. I, 3I plus minus 1I. If you add them together, it gives you 2I. Do the J own. Minus J plus J plus 2J. It should give you J. So we have I plus J. So do the same thing for K. 3K minus K. It should give you 2K. So we have that our A plus B is equal to I plus J plus 2K. I plus J plus 2K is our A plus B. So then now, if we now want to carry the dot product of these two things now, if we want to carry the dot product of these two things now, the dot product will now be trying to take what you got from A and multiply what you got from B. And that way you'll be multiplying 3 times I. That's we said that our I component for the A plus B was 1I. So 3 times 1I is going to be giving us 3. Because I times I, when you multiply components, that is 3I times 1I. If you multiply any two vectors that have I and I, it would cancel out to remove the I. J times J is going to remove the J. K times K will remove the K. So 3I times 1I will remove the I, and 3 times 1 is going to give us 3. So now 5J times 1J, 5J times 1J is going to be giving us 5. So we have 3, 5. So then what they call it, minus 3K times 2J, minus 3 times 2 is what? 6, if I'm correct. Minus 3 times 2 is minus 6. So minus 6, if you should sum, I don't know, I'm losing these numbers in my head, Sha. So if you should sum, if you should do this stuff that I've been explaining, you're supposed to get an answer that's giving you minus 7. I don't know if anybody was following me or was writing it on their notes. Hello? Hello, can anybody
Hello,
hear
sir.
me? Yeah?
Yes.
We can hear you, sir.
Was anybody following what we're trying to calculate?
Yes, sir, but I was not writing
Okay, so the idea is just to do the addition first. Once you've done the addition, it should give you another vector that has I, J, and K. Then you multiply the I, J, and K components, I to I, J to J, K to K. What's to give you? It will give you just ordinary number, because when you multiply I and I, it will remove the I. Multiply something that has J and another thing that has J, it will remove the J. When you multiply another thing that has K and another thing that has K, it will remove the K. So that's how you multiply. When you multiply it, when you check your final answer, you should be getting a value that should be equal to minus 7. So I don't know if you guys were following that though, but if you were following, that's just how you would carry the solving out. And because of it is giving you something that does not have I, that's why we say it is giving you a scalar, because those I, J, and K, I said they represent X, Y, and Z, and that X, Y, and Z, they are directions. X points side, Y points up, Z points inside the book. So that way, we don't have direction here because we don't have any I. So that's why we said when you carry out dot products, it will give you a scalar. That is something that does not have I or J. So in case you saw something like this now, and you saw the option had something like 3I, 4J, 5K, 7, or minus 7, without even calculating, because of that dot products should always give you something that does not have I, J, or K. You can know that, okay, the correct answer without solving is this. So that is just typo. That's something that you should just put at the back of your mind. Dot products does not give you I, J, or K in its own final answer. But cross products will always give you I, J, and K. So that is that. So that is that one. So now let's move to magnitudes of vector. Magnitude of vector, trying to get the magnitude of a vector. So as we know that vectors, let's say we have a vector A having its I component, J component, and K component. To get the magnitude of that vector, we will take the values that is behind the I component, square it, plus the value behind the J component, square it, plus the value behind the K component, square it, then add them together. Then once you've gotten the sum of everything, you now take the square root. By taking that square root, you are getting the magnitude of that vector. You're getting the magnitude of that vector. So I don't know if you've been following me, if you've been listening to what I'm saying. I would like someone to get the magnitude of a vector that we have here. We have a vector of 2, 4, 1, where 2 is the I component, 4 is the J component, 1 is the K component. So based on this formula and what we have here, find the vector magnitude, the magnitude of the vector. The I component is 2, the J component is 4, the K component is 1. Is anybody solving at all? Hello?
Hello, sir.
Yeah.
Yes, sir. I'm talking.
Okay. I think we are even behind time. Let me see if I would do it here. So 2 squared is 4. 4 squared is 16. 4 times 4 is 16, yeah. 1 squared is 1. So
So I got
4 plus,
4.5.
okay, let's see whether it's correct. Let's see whether it's correct. 2 squared is what? 2 squared is 4, Shay.
Yes, sir.
4 squared is 16, right?
Yes, sir.
1 squared is 1. So 16 plus 4 plus 1, that should be 21. Shay?
21. Yes.
So square root of 21 is what? That should be our answer. Square root of 21 should be the answer. So if it is 4.5, then that's very well of you. But if it's not 20, if it is not 4.5, then probably there was an error you made somewhere, and that's very okay. Because even myself, sometimes I make errors in computation, even when it is obvious sometimes. So square root of 21 is the answer for this one. If you punch it in your calculator, whatever it gives you should be, let me see, 21. 4. It should be correct now. It should be correct. 4 times 4 is 16. So you should be correct. I think you should be correct. That person that said 21 should be correct. Someone should punch root 21 on your calculator. You should be correct. I think you should be correct. Has anybody punched root 21 on their calculator? Has anyone punched root 21 on their calculator? Hello?
4.58.
Yeah, so your answer is very correct. So that's the answer for that. I don't know if anybody has any question for us as we move before we call it a wrap today.
No
Because I think we've got
question,
people.
sir.
You said what? You said what?
No question. No question.
More questions. Don't worry. What would happen is there would be a question, a form I would send. I would send a Google form this evening. Oh, I think, okay. I'll send a Google form this evening based on everything we've done this evening. So based on everything we've done this evening, you would solve the form for today for physics. So I will not say anything, Sha. You will solve the form. Then I would see the highest by tomorrow morning. I'll see the highest by tomorrow morning. Or you paste your answers for those of you that are on the call. I don't know. Okay. I don't know. I don't know. I don't know. I don't know. If you are not already on our group yet, or if you just joined this class, probably from a friend, if you're not on the call, if you just join the class, you're not part of the team, the group. If you see your friend's own, maybe your friend's email was the one that came first, or you got first. By tomorrow, just let me know when I post the links of people or the list of people that scored whatever they scored and the highest. So once you see who is the highest, just let me know. So that'll be all for this evening, and I'll be saying good night to everyone.